Mechanical properties of solids. Deforming force. If we have an object and we can change the configuration of this object either by applying force or some other mean, it is called as deforming force. If we are applying force and deforming or changing the configuration of the object, then we say this is a deforming force. What is elasticity? It's a property, it's a characteristic of an object by virtue of which it regains its original deformation after the removal of deforming force. That means, say, if there is a spring, now you press it from here with some force and this presses down. Once you remove the force, it will regain its original configuration. So this property is known as elasticity. What is elastic limit? It is known as the upper limit or higher limit of deforming force up to which, if deforming force is removed, the body regains its original form completely. But if beyond that, if that is a force, and if you are pressing beyond that force, then the body loses its property of elasticity and it will not regain its position or configuration. It will be permanently deformed. This is called the elastic limit. Perfectly elastic bodies. Those bodies, the original configuration, if it can regain immediately and completely, if the force being applied is removed, these are known as perfectly elastic bodies. For example, quartz, phosphor, bronze, these are perfectly elastic bodies. Perfectly plastic bodies. So there is a difference between elastic and plastic. Those bodies who are not going to regain its original configuration at all. If you press it, if you apply some force, after that it will not regain its original configuration or original shape, you can say. These are known as perfectly plastic bodies, like putty, like paraffin, wax. Stress. What is a stress? This is an internal restoring force acting per unit area of a deformed body. So there is a stress in a body. So there is a stress in a body. This is the internal, see, it is an internal restoring force, which is for an area. This force is acting per area of a deformed body. This is called stress. So stress is simply given by the restoring force. Please understand, it is a restoring force per unit area divided by area. And since this is in Newton, this is in meter square, so the unit is Newton per meter square, or you can say Pascal. Force is given, this force upon area is generally spoken as the pressure. So it's Pascal, and the dimensional formula is this one. This is a tensor quantity. Stress is a tensor quantity. Stress are of two types: normal stress, tangential stress. Normal and tangential stress. If the deforming force is applied normal to the area, like this is the area, normal to the area, then the stress is called normal stress. If there is an increase in length, the stress is known as tensile stress. If there is decrease in length, then we are applying a compression stress. So if this is an area, you are applying force like this, and if the length is increasing, this is tensile strength. If it is something like this, you are pressing it, it is changing its length or decreasing its length, then you are applying, or you can say this stress is compression stress, which is developed inside the body, which is restoring force divided by area, per unit area. Tangential stress, if this is a body and you are applying the force tangentially or deforming force tangentially, then this is a tangential stress. Strain. What is a strain? Strain is a fractional change in configuration. That is, you can have a equation, or you can say a relationship, that strain is change in the configuration divided by the original configuration. Means what is the change which has happened, say delta change, divided by what was the initial one, say initial one. So it has no unit because these both are same, and it is a dimensionless quantity. In accordance with the change in configuration, because we are talking about the change in configuration, the strain is of three types. Longitudinal strain, volumetric strain. So this two, and of course we have a shearing strain too. So let us see what is longitudinal strain. This is change in the length. So when we have a change in length divided by original length, or change in length with respect to the original length, this is the longitudinal strain. If there is a change in volume, so if there is a change in volume that with respect to the original volume, then this is the volumetric strain. Shearing strain, that is the angular displacement of a plane which is perpendicular to the fixed surface. Angular displacement of the plane which is this is a plane perpendicular to this plane. So there is an angular change, angular displacement, or you can say angular displacement of the plane perpendicular to the fixed surface. So if you apply a deforming phase, it may change its position like this. So this is the angle. This is the shearing strain. Hooke's law. There is a limit of elasticity. So within that limit of elasticity, the stress is proportional to the strain. So this is proportional sign. Stress is proportional to strain, but it has to be within the limit of elasticity. If you remove this proportionality sign, it will be stress is equal to E into strain. E is the modulus of elasticity. So for different materials, different bodies, there are different modulus of elasticity. This is Hooke's law. What are the types of modulus of elasticity? Young's modulus of elasticity, bulk modulus of elasticity. So Young modulus of elasticity, which is represented by Y, this is the ratio of normal stress to the longitudinal strain. Normal stress to the longitudinal strain, but this has to be within the limits of elastic limit. So Y is given by normal stress divided by the longitudinal strain. Normal stress can be given by F into delta L, and this is of course A into L, which gives you this expression. The unit is, because we know that stress has the unit Newton per meter square, which is Pascal. Strain is a dimensionless quantity, so the dimension formula is ml minus 1 t minus 2. The bulk modulus of elasticity, this is given by K, which is the ratio of the normal stress with respect to, this was longitudinal strain, and here in the bulk modulus it is volumetric strain. So again the same thing happens, that it has to be between the elastic limit. So K is given by normal stress divided by the volumetric strain, and this is of course F into V by A delta V, because volumetric strain, and we know that we have talked about delta V by V. This is change in the strain. Volumetric strain is change in the volume with respect to the original volume. So this delta V by V goes up. So F by A divided by delta V by V, which gives you this one. So this delta P here, this is delta P, and delta P is what? This is delta P V delta V. Delta P is simply this F by A is delta P. So this eventually becomes delta P V by delta V. Delta P, force per unit area, is the change in pressure. Again, because it is stress by strain, strain is dimensionless quantity, unit is Newton per meter square Pascal, and again this one same as the Young modulus of elasticity. Modulus of rigidity given by this sign, eta you can say. This is the ratio of tangential stress to the shearing strain. And again it has to be between the elastic limit. See, every time it has to be between elastic limit. Eta is given by tangential strain divided by shearing strain, and it is also given in the unit is Newton per meter square Pascal, and dimension formula is again L minus 1 T minus 2. Compressibility. Compressibility of any material is just you take the reciprocal, invert the bulk modulus of elasticity. So if this is K, bulk modulus of elasticity, if you take 1 by K, that is the reciprocal, this is the compressibility. The SI unit is the inverse of K, that is Newton n minus 1 and m square. CGS unit is dyne minus 1 and centimeter square. 1 by Newton called as dyne. So steel is more elastic than rubber. You'll be surprised to know steel is more elastic than rubber. Solids are more elastic and gases are least elastic. This is a surprise, but it is in the terms of these definitions. Solids are more elastic, gases are least elastic. And for liquids, the modulus of rigidity is 0. The Young modulus Y, the modulus of rigidity, these are possessed. They are only in solid materials. What is the limit of elasticity? When you are applying some force, say it is a deforming force. So the maximum, say F max, maximum value of that deforming force for which the elasticity is present in the body, or it is present in the body, is called its limit of elasticity, after which the elasticity ceases to be present. Then we have crossed the limit of elasticity. Breaking stress. The minimum value of stress we need to require, or which is required to break a wire, is the breaking stress. This is fixed for a material, breaking stress, but the breaking force will vary because it depends on the area of cross section of that wire. So there is a safety factor which is related with this breaking stress, which is breaking stress divided by the working stress. Elastic relaxation time. What is this time? There is a delay of time in restoring the original configuration after the removal of deforming force. This is called elastic relaxation time. What happens is, when you deform something, apply deforming or some force, then it takes certain time to for an object to come to its original configuration. This is the elastic relaxation time. For quartz and phosphor bronze, this time is negligible. Elastic after effect. There is a very short, or you can say temporary delay in regaining the original configuration by the elastic body after the removal of this deforming force, and this is called as elastic after effect. What is this called? Elastic after effect. Elastic fatigue. This is a property of elastic body by virtue of which its behavior becomes less elastic under the action of repeated alternating deforming force. This is known as elastic fatigue. Now just relate it with your normal life. At morning, at around 7 or 8 o'clock, when you get up, you are very fresh. By the evening, if you are doing same work again and again, you are tired, you have fatigue. And this is true with anything which is present in the world. So the property of elastic body by virtue of which the behavior becomes less elastic, because you are applying, or there is an repeated alternating deforming force, and this is elastic fatigue. Ductile material. The materials which show large plastic range beyond elastic limit is called ductile material. See, copper, silver, iron, aluminum, these are all metals, or you can say near to metal, and they are showing ductility. So material which show large plastic range beyond the elastic limit also, these are known as ductile materials, and these are used to make springs and sheets. Brittle material. The material which show very small plastic range beyond elastic limit. See, this is just the opposite. The material which show very less, here it is, they are showing large plastic range beyond elastic limit. Here they are very small plastic range beyond the elastic limit, and they are brittle. Glass, cast iron, you break glass or you just hit a glass with normal force, very less force, it will break. Elastomers. Elastomers, the materials for which strain produced is much larger than stress applied. Again, the materials for which strain produced is much larger than stress applied within the limit of elasticity. These are known as elastomers. The rubber, the elastic tissue of aorta, the large vessels carrying blood from heart, these are elastomers, and they have no plastic range. Elastic potential energy in a stretched wire. So the work done when you stretch a wire, so there is a work done in stretching a wire, which is stored in form of potential energy of the wire. So potential energy U can be seen as average force into the increase in length, which is half of the force and increase in length. That is half into stress into strain into the, because what we are talking about wire, so volume of wire. So there is elastic potential energy per unit volume, U given by half into stress into strain, and this is Young modulus into strain square. The elastic potential energy of an, or you can say a stretched spring, is half kx square. K is the force constant of spring, x is the change in length. Thermal stress. When temperature of a rod fixed at its both end is changed, a rod fixed at both of its end, if the temperature is changed, then a stress is produced, and this is called as thermal stress. So thermal stress is given by force upon area, which is y alpha delta theta. This alpha is the coefficient of linear expansion of the material of the rod, and when the temperature of gas enclosed in a vessel is changed, say if there is a vessel and there is a gas, the temperature is changed, then the thermal stress which is produced, this is known as, or you can say, because gas will change the pressure, so the thermal stress produced will be equal to the change in pressure, delta P. So you can say delta P, that is the thermal stress, is equal to Ky delta theta. K is bulk modulus of elasticity. We have gamma also, which is the coefficient of cubical expansion of the gas. There is interatomic force constant K, which is given by YR0. R0 is of course the interatomic distance. Poisson's ratio. When a deforming force is applied at the free end of a suspended wire, see there is a suspended wire, say of length L, radius R, then there will be increase in length, say dl. But as the length, see this is the wire, if I increase the length, it will be like this, but the diameter, there will be increase in length, say this much, but the diameter will decrease. So length increases by dl, radius decreases by dr. So there are two types of strains are produced by a single force. This longitudinal strain is this delta U, or you say lateral strain, is delta R by R. So the Poisson's ratio is simply lateral strain by longitudinal strain. So if we divide these two, we get delta R by delta U. Theoretically, the Poisson's ratio lies between -1 to 0.5, but the practical values will lie somewhere between 0 and 0.5. What is the relationship between Y, K, eta and alpha? Y is given by 3K 1 minus 2 sigma. Y is given by 2 eta 1 plus sigma. Sigma can be given by 3K minus 2 eta by 2 eta plus 6K. 9 by Y is equal to 1 by K plus 3 by eta, or you can say Y equal to 9K eta by eta plus 3K. There are certain things which needs to be remembered, important points, that the coefficient of elasticity depend upon the material, its temperature, purity, but not on stress or strain. For the same material, there are three coefficient of elasticity, gamma, eta, K, have different magnitudes. The isothermal elasticity of gas, which is given by ET, is rho, where rho is the pressure of the gas. Adiabatic elasticity of gas ES is gamma P. Gamma is simply Cp by Cv, which is the ratio of specific heat at constant pressure and constant volume. The ratio between isothermal elasticity and adiabatic elasticity ES by ET, gamma is given by Cp by Cv. Cantilever, a beam clamped at one end, see, this is one end, and it is loaded at free end. This is known as cantilever. So the depression at free, because there is a depression, this is given by this del sign. The depression at the free end of cantilever is given by, if this is the length, this is the weight, WL cube by 3YIG, where W is the load, L is the length of the cantilever, Y is the Young modulus of elasticity, I sub G is the geometric moment of inertia. If we have a beam, rectangular cross section having breadth B and thickness D, IG is given by BT cube by 12. And for a beam of circular cross section having a radius R, IG is given by pi R to the power 4 by 4. Beam supported at two ends. These are two ends, beam is supported in between, and it is loaded at the middle. The depression at middle, delta, is given by, again, this is W, this is L cube, and we have various other things with YIG. Torsion of a cylinder. Please observe this diagram very carefully. Here the torsion, eta, this couple per unit twist, C, is given by this pi eta R to the power 4 2L. And this eta is the modulus of rigidity of the material of the body. This R is radius of cylinder, and L, of course, is the length of cylinder. So the work done in twisting the cylinder through, say, angle theta, we are twisting it with angle theta. So this is angle theta, which is given by W1 by 2 C theta square, and there is a relationship between this angle of twist and this angle of twist theta and this phi, angle of shear, which is R theta equal to L phi. You can say phi equal to R by L theta. Structural steel rod has a radius of 10 mm. So radius is given, the length is also given, 1 meter. 100 kilonewton force stretches it along its length. So there is a rod, and this is stretched along its length. We have to calculate the stress, the elongation, the strain. The Young modulus of this steel is given by 2 into 10 to the power 11 Newton per meter square. We assume that this rod is held by a clamp, say at one end. So the force which is applied at other end, which is parallel to the, this is the length, so it is parallel to the length of the rod. What will be the stress on the rod, which is stress is simply force upon area. Area is pi r square, this is the cross section area. So F by pi r square, force is given, we can write 100, and then kilo, for that we write 10 to the power 3. Then the pi 3.14, r square, radius is also given, so we can convert it into meter and write here. That will come around this number. Then to find the elongation, we know that this delta L by L is given by, again, the stress, you can say F by A 1 by Y. Essentially Y is given by this number, F by A, and delta L by L, that is the linear elongation. So we will find out this delta L using this expression and put all these values. Force is known to us now. This force by A is given to us because we just found out this value. So we can directly put it here. And then we have L, which is 1 meter. Directly we can put it, and the Y is also given. So this comes to around 1.59 millimeter. And the strain, of course, is this one. So strain is given by delta L by L. Delta L is, we just found out, L is given as 1 meter. So this is around 0.16%, or this is the value. Okay. A copper wire of length 2.2 meters, so length is given, and a steel wire, so there is a copper wire and there is a steel wire of length 1.6 meter. This length is also given, both of diameter 3 millimeter. They are connected end to end. When they are connected end to end like this, this is C, this is S. When stretched by a load, they are stretched by a load, the net elongation is found to be this much, 0.70 millimeter. We have to find out the load being applied. So these two wires, they are under what? They are under tensile stress, because they have the same tension. Because the question, it is being said that they have equal load W and they have same area cross section A. So we have a expression, Young modulus is given by stress by strain. How to find out? We know all these values. This is given by W by A, and the strain is given by the stress, strain, and Young modulus. All we know, we will just put this value. Stress is W by A, Young modulus is YC, strain is delta LC by LC. This C is for copper, and same thing we have done for the stainless steel. So we can just equate these two. When we equate these two, we can get delta LC by delta LS. We'll take this and this on the one side, others on the right hand side, and we know the values. LC we know, LS we know, and from the table we can always find out the Young modulus of C and S. So we'll put this value and we find out this delta LC by delta LS as 2.5. Now what is the total elongation? Say delta LC for copper and say delta LS for steel. So just add them, we get the total value. When we solve the equation, because we have this equation, one equation is delta L by delta S is this one. The total elongation delta C by delta LS is given by 0.7. So we have two equations. We solve this, we get delta LC and delta LS separately. So this is 5 and this is 2, and of course with the value of 10 to the power minus 4 meter. And how about this? How to find this W? Because we know about these now. Any of this equation you can take. So let us take the copper one. Now we have to find this W, which can be taken from this expression we have already seen. Then we just have to put the area pi into r square. Radius we have to take this for this one. For copper one, YC is also known. Delta LC we have just found out. LC is also known. And we just put the value and we get W. That is the load being applied. In a human pyramid, this is a human pyramid. In a circus, The entire weight of the balanced group is supported by the legs of a performer who is lying on his back. See, this is the guy on the back. The combined mass of all the person performing the act and the tables, plagues, they are this one, this is 280 kg. The mass of performer lying on his back at the bottom of the pyramid is 60 kg. Each thigh bone, that is a femur, of this performer has a length of 50 centimeters. So it has 50 centimeter. And effective radius, this radius is around 2 centimeter. We have to determine the amount by which each thigh bone gets compressed under the extra load. So when this all load is on this thigh bone, what is the compression? So how we are going to do this? The total mass of all the performer tables and plagues is 280, mass of the performer is 60. So what is the mass supported by the legs of the performer at the bottom of the pyramid? We have to subtract these two. That is 280 minus 60, that is 220 kg. Now what is the weight of this supported mass? Because this is only 220 kg, we have to find out the 220 kg weight, because the gravity is also working downwards. So 220 into 9.8 gives you 2156 Newton. And the weight supported by each thigh bone, because there are two thigh bones, so we have to divide it by 2. So we get 1078. The young modulus of young modulus Y of bone is 9.4 into 10 to the power 9 Newton per meter square. The length of each thigh bone is also given 0.5. The radius is also given 2. This is given in the question itself. So this is we have transformed into converted into meter, and 2 centimeter, let it be like that. We'll also change the this 2 centimeter because we need all in meters. So the cross-sectional area approximately of this thigh bone is given by pi. Then we'll use this radius. So it will be pi r square. And of course we know that the Young modulus is given by stress upon strain. Stress is F by A, strain is delta L by L. So delta L can be found out using F into L by Y into A. Put all these values because we have found out these values, and this will be around this number. And this is a very small change. The fractional decrease in the thigh bone can be obtained by delta L by L. So this is around 0.0091%. The average depth of Indian Ocean is about 3000 meter. We have to calculate the fractional compression delta V by V of water at the bottom of the ocean. Given that the bulk modulus of water is this much, we have to take G as 10. Now, the pressure which is exerted by this much or 3000 meter column of water on the bottom layer. So, water is all around. So, what is the fraction of this layer on this layer? This is given by pressure. We know this is rho hg. So, we'll use all these things, 300 meter, then the rho, this is height, this is rho, and this is the gravity. So, this comes to this number, and we know that the fractional compression delta V by V is given by delta V by V. Again, we have to use the bulk modulus. Bulk modulus is given by the value which is stress by the delta V by V, that is stress by strain, and strain should be the bulk or change in the volume, the fractional change in the volume. So delta V by V can be found out using stress by V. Stress is of course this number, then V is given here. Just divide them, you get 1.36 into 10 to the power minus 2 or 1.36%. Let us summarize. The stress is restoring force per unit area, and strain is the fractional change in dimension. It can be delta L by L, it can be delta V by V. So there are three types of stresses: tensile strength, which is longitudinal stress, of course, which is associated with the stretching, or you are compressing, compression and stretching. We have shearing stress and hydraulic stress. For very small deformations, the stress is directly proportional to the strain. The stress is directly proportional to the strain of many materials. This is known as Hooke's law. The constant of proportionality, this proportionality can be changed, and we can put a constant here, which is the modulus of elasticity. So three elastic moduli we have: Young modulus, shear modulus, and bulk modulus. These, they describe the elastic behavior of object as they are responding to the deformation force which are acting on them. And the solids which belong to a category or a class called elastomers, they do not obey Hooke's law. Then when an object is under, say, some tension or a compression, the Hooke's law can take form like this. We see this is very important for solving the problems. F by A is equal to Y delta L by L. This essentially has come from Y. Y is F by A by delta L by L. This delta L by L is the tensile or compressive strength. So you can say it as a strain. And F by A, the F is of course the force or magnitude of the force applied causing this strain. A is the cross-sectional area over which this force is applied, which has to be perpendicular to A, and Y is the Young modulus of the object. So the stress, this is the stress, so you can write it as stress. So this is stress by strain. This is very important. You just have to remember that Y is stress by strain. Other things will be solved. A pair of forces when applied parallel to upper and lower faces, the solid deforms so that the upper faces move sideways with respect to the lower. The horizontal displacement delta L of the upper face is perpendicular to the vertical height L, and this type of deformation is called shear. Means a body goes like this. This is a shear example. And corresponding stress is known as shearing stress. So this type of stress is possible only in solids. In this kind of deformation, the Hooke's law takes a form, but here we have to have this G, Y is replaced by G. G is shear modulus. The things remain same. This is force, this is area, this is change delta L, displacement of one object, end of the object in the direction of the force being applied. Original length is this. When an object undergoes the hydraulic compression due to stress exerted by the surrounding fluid will also exert some pressure. So Hooke's law takes form like this. P is the pressure, which is the hydraulic stress, which is given by capital B delta V by V. This P is the hydraulic stress on the object due to fluid. Delta V by V is the volume strain, and this is the fractional change in the object volume due to the pressure. And this B is the bulk modulus of the object. So this is the brief idea about the mechanical properties of solid. Thank you so much and take care of yourself.